So we are now working with the randomization-based test. And this type of test is a permutation test. The difference between bootstrapping and permutation is bootstrapping, when you bootstrap, you sample, you record, and you replace. Here, when you sample, you're going to be placing into groups, and you don't replace from the original pool of information. And so, because you aren't replacing, it's referred to as a permutation test. Permutation in statistics implies order matters. And so, you're dealing with different orderings of all of the possibilities. So let me read through this, and so you get what's going on. The randomization-based test is a permutation test that approximates the null distribution of the difference in proportions by simulating many samples from a population in which the null is true. Okay. For a difference in proportions, the test is called a permutation test. Each simulation starts with the original sample. So our original sample we take, okay, the values of the response variable are randomly shuffled. They're permuted. Okay, so we take our sample and we shuffle it all around so that neither group should tend to have a higher proportion of teens that text every day than in the other group. This is equivalent to taking, this is the way this works. You have the 5,396 note cards, each representing a case in the sample. So there's 519 yeses, and then there's 4,876 no's. Now, I'll come back to this. So we're back up here to this table, and here's our yeses, and here's our no's. Okay. Did I go too far? I might have. Yep, I did. I went too far. Okay, here we are. So you shuffle the note cards and divide them into two groups of 4,387 cards and 1,008 cards. And you calculate the difference in proportions for the two groups. And then you repeat this process many times to build a null distribution of the difference in proportions. So let me take these two numbers and scroll back up for a second. Okay, so where are the 4,387 and the 1,008 coming from? Well, these are our totals. Okay. Now, let's scroll back down. Where are we at? Oh, we're back here. Now, we're going to use the two proportions hypothesis test analysis in the randomized model. So we're going to click here. We're going to go to our randomized model, and we're going to go to two proportions hypothesis test. Now, our rows column will be the helmet indicator, and then our column, our rows column, I'm sorry, our rows will be helmet indicator, and then our column will be text indicator. And there's our same setup again. Okay. Now, we want to make sure that we compare rows. Okay. So we are comparing our no helmet group to our helmet group. Our alternative hypothesis should be that group 1 is greater than group 2. All right. Now let's make sure we're matching this up. So we got to go to simulations. If we do 1,000, I'm sorry, if we do 100, and we click on our seed, we should get a distribution that looks like that. But your work is requesting, or you're trying to demonstrate 1,000. So we have a histogram. So we're going to click on 1,000, or we're going to put in 1,000. We're going to go ahead and hit histogram. It takes a minute. So our p-value is incredibly small. Since our p-value is incredibly small, we're going to reject the null. Okay. We're going to operate as if the alternative hypothesis is, I'm going to say, correct. We just say really that the data supports the alternative hypothesis. Okay. And is there anything else that I'm missing? No, we're okay there. Confidence interval for proportions. You can again do what we did before, where you take your 0.050, your p hat, your sample statistic. You have the critical value, or your multiplier, done as we did before, the 1.96, and you use the standard error. However, again, we are assuming that we no, wait. Yeah, that's what I'm trying to say. We are not assuming that the null is true when we calculate the confidence interval. And so what we do for our standard error is we have our p hat no helmet, 1 minus p hat no helmet, and then the n for no helmet, and for helmet, and then we get a standard error of 0.00860. Again, I said the 1.96, and this is our model-based confidence interval. We can create the 95% confidence interval by simulation, and again, it's called the bootstrap percentile confidence intervals for two proportions. So let's go to that and just demo where that's at. We randomize. We have two proportions confidence interval. Okay. In our rows, again, helmet indicator, and then our text indicator. There we go. Now, bootstrap percentile, 95%. And again, if we're looking at it from that perspective, where we just have, I believe I have 100 up there. Let me just double check simulations. Yep, we got 100, and we're on dot plot. We're at 0.032, and then the upper is 0.067. My hunch is that we're going to go to 1,000, and we're going to go to a histogram. So we're going to change this to 1,000. We're going to click histogram. And we just got to wait a minute for it to occur. And there we go. So our 95th percentile, or 95th confidence interval, here is 2.5th percentile, and here's 97.5th percentile. And those values are 0.035 and 0.066. Do I have the seed? Oh, what did I just do? Oh, there it goes. Do I have the seed on? I don't know that I have the seed on. I do not have the seed on. You know what notice what happens. We have slightly different results if we don't have the seed on. So I'll click the seed on, and let's see if we get the same results as what the guide says. And we do. All right. Note that the 0 is not in the interval. Well, where's the 0 coming from? The 0 is coming from our null hypothesis way back up here. And since the 0 is not in there, we're indicating that the alternative hypothesis is being supported by the confidence interval result. All right. That's a lot of videos for you. I apologize that I had to break them up as much as I did. All right. Everybody have a good night.